All right, folks, here we are. We're continuing to learn about exponential growth and exponential decay. We have discrete exponential growth and discrete exponential decay. We also have continuous exponential growth and continuous exponential decay, right? So here's our four formulas. You have to know which one goes with which. The E goes with continuous. Think about this. You'll see the word continuously, right? Continuously, right? Okay, so whenever you see the word continuously, we're looking for one of the E formulas, okay? If it's growth, the R is positive. If it's decay, the R is negative. If it doesn't say continuously, then you won't pick the one with the E. You'll pick one of these two. If it doesn't say continuously, then it's a discrete growth formula. If it's a discrete growth or decay. Growth is going to have the plus, decay is going to have the minus. So let's do a few examples here real quick. Let's say that you have some population of 3,000. Okay, so the population currently has 3,000. It's growing at a rate of 7% per year. So that's 7% per year. It's growing quarterly, okay? So quarterly. And we want to know how many will there be after 12 years, okay? So 12 years, all right? Well, it says quarterly. It doesn't say continuously, so it's a discrete. And it says it's growing at 7% per year, so it's a discrete growth. So we're going to do P times 1 plus R over N to the power of NT. You're going to need a calculator for this, okay? Just grab a calculator. Step one is plug all the numbers in. So we're going to put a 3,000 in for P. So P, 3,000, then a parenthesis, then a 1, then a plus, R over N. Okay, in this case, R is 7%. But we have to turn 7% into a decimal. So I'm going to do 7 divided by 100, and I get 0.07. So 0.07 divided by N is how many times does it grow in a year? Well, it's growing quarterly. How many times in a year does quarterly happen? That's 4 times a year. So I'm going to put a 4 here, close the parenthesis, to the power of N times T. Well, N, again, we already saw it. See this? Whatever number is down here is going to be up here. So 4 times. T is how long is it growing? How long are we looking out at this growth? And it's remember T is dependent on the per time value for the rate. So how many years? Well, they told us 12 years. So we're going to put a 12 here, right? That's step one. Plug everything in. Step two, simplify the formula. Here's what you want to do. You have to simplify this. You want one number here. You don't want that as a formula. And you want one number here. Before we calculate anything, we got to simplify this. So the 3,000 is going to stay as 3,000. Then in our calculator, we're going to key in 1 plus 0.07 divided by 4. So you can see what it looks like, okay? I got 1 plus 0.07 divided by 4, and when I press enter, I get that number. I get 1.0175. So I'm going to put a 1.0175 in there, okay? To the power of whatever 4 times 12 is. Well, 4 times 12 is 48. You can use a calculator if you want to. And now that we have simplified our formula, now we can key it into the calculator. Now here's what you have to understand. You cannot do this times this and then this. Remember the order of operations. Parentheses, then exponents, then multiplication. We have to do this first. We have to do this first. The exponent has to be done first. Then, after doing the exponent, then you can multiply by 3,000. So, now you could actually, if you have a scientific calculator, you could just key the whole thing in. Just make sure you use the, parentheses. Well, you don't have to use the parentheses now, but I would, okay. I would use the parentheses so that the calculator does this first, then have the 3,000. So I'm going to key in 1.0175 to the power of, and you might say, well, where's the to the power of button? It's this one that it looks like an upward arrow. It's called a caret. So if you hit that button, it goes to the power of 48. Then I'm going to press enter. Now I'm going to multiply by 3,000 times 3,000, and that gives me 6,898 point. I'm going to go maybe 3 decimal places, 796. And it really depends on how large your number is. Sometimes I won't go any decimal places, okay? But I'm going to go ahead and do that for now just in case, okay? And I can always round it to 6,899 if I want to. I could even call it 6,900, okay? Typically, if you're close enough, for now, let's just go to a couple decimal places, all right? So there we go. There's a problem where we calculated the population after 12 years of growth. So the population started at 3,000, and after growing quarterly at 7% per year, after growing for 12 years, now there are almost 7,000 in that population. And that population could have been money, $3,000 that turned into $6,900. That population could have been humans on an island. That population could have been bacteria or deer or all kinds of interesting things. Okay, it's probably money because it's growing quarterly. Remember, living things typically grow continuously. Okay, let's try another one. So let's say that we have 10,000 of something growing continuously. All right. At 3.5% per year, and we want to know how many there will be after 5 years. 5 years. Okay, well, it's growing, and it's growing continuously. It's growing, therefore the R has to be positive. It's growing continuously, so we got to pick one of our two E formulas. These both have E. This one has a negative R. This one has a positive R. It's growing, so we're going to pick this one, the PERT formula. So in for P, we're going to put 10,000. So 10,000. Then we're just going to put an E. That's it. We're putting an E. To the power of R. R is 3.5%. Well, 3.5%, if we do 3.5 divided by 100, that'll be 0.035. So we're going to put e to the power of 0.035 times t. And t is 5 years. So times 5. Okay? Now, it's not imperative in this situation for you to simplify the 0.035 times 5, but if it makes you feel better, let's go ahead and do it. We'll go 0.035 times 5. That gives us 0.175, or just 0.175. So this is 10,000 times e to the power of 0.175. And so now we're going to type in, watch this, we're going to type in 10,000, and then we're going to press second and then the ln button, and that'll give us an e to the power of, okay, and then we'll put in 0.175, okay, and then we'll press enter, and we get 11,000 something, right? 11,912.46. I'll say 462. All right? So, continuous growth for 5 years at 3.5% per year. Started with 10,000. Here's our formula, and we end up with, now there are 11,912. And that could be, I don't know, that could be alligators, or it could be beavers, or humans, or something. Okay? It's a population growing. And this is how populations grow, typically exponentially. All right? All right, let's see here. Let's do a couple more examples, because I want to do at least one of each. All right, let's say that there is a population of something, and let's say that there are 300,000 of them. And they are dying continuously. Dying continuously at the rate of 7.42% per hour. Per hour. We want to know how many there are going to be after 48 hours. How many will there be after 48 hours? Remember, this is 7.42% per hour. Okay, so that means that the time variable is hours. And since we're asking about 48 hours, we're going to put 48 in for time. Now, because it's continuously, it's going to be one of these two formulas, because they both have e's in them, right? But it says they're dying continuously. Dying means that their value is getting smaller. If the value is getting larger, that's a growth formula. If the value is getting smaller, that's a decay formula. Okay? So because this is dying continuously, we know it's going to be PE to the negative RT. So P is the starting value, and in this case, that's 300,000, right? So 300,000. Then we're just going to put an E, because E is a number, right? Like pi. Put an E to the power of negative R. Well, what is R in this case? R is the decimal version of 7.42%. Well, that would be 7.42 divided by 100. Or we can just move the decimal point over 2 places, which would give us 0.0742. But remember, this is negative R. So this is to the power of negative 0.0742 times T. T is in hours, and we want to know how many after 48 hours. So times 48 equals. So let's simplify this. Let's do negative 0.0742 times 48. That gives us negative 3.5616. So this is going to be 300,000 times e to the power of negative 3.5616, which we can just plug into the calculator. So let's see here. We'll do 300,000. Second ln gives us e to the power of. Then we'll put in negative 3.5616. Press enter, and we get 8,518. That's a lot less, right? That's a lot less than what we had. It started at 300,000. They were dying and dying and dying and dying. And now there's only 8,518 of them left. It does say 0.007. But that's barely much. We'd probably just round that to a whole number. 8,518 of them left. There were 300,000 of them. Well, this could be bacteria. Let's say it's a bacteria after an antibiotic has been administered, and so those bacteria are going to die off and die off and die off because that antibiotic is going to kill a whole bunch of bacteria, right? All right, so that's it. We got one more to do, right? One more example. All right, let's do our discrete decay. Let's say that we have some population. Let's say that we have a population of 24 million. 24 million, okay? And it's decreasing at the rate of 0.73%, okay, per year. And it's compounding monthly. And we want to know how much there will be left after 27 years. After 27 years. All right, here's something I want to teach you. Here's something I want to show you. You got to think about this. Well, first of all, it's losing, it's decreasing, right? So it's going to be a decay. Because it doesn't say continuously, it has to be discrete. And if it's losing value, it's going to be the one that has the minus, right? So this is our formula. So when we write out the formula, we want to put in P, the starting value. But instead of putting in 24 million, right, which is going to be a real pain, did you know that you can just put in 24, just put in 24, do the formula. When you get an answer, just put the word million on there. Okay, it's going to be a lot easier for you. And you got to learn how to do that, because there are a lot of things in this world, especially in the economy, that when you're dealing with large numbers, you don't actually put out all of the numbers. You just throw on a million or a billion or a trillion. You just throw the units right on there. Okay, so we're just going to work with 24. So 24 parenthesis 1 minus the rate R, 0.73%. Now, don't put 0.73 because it's not 0.73. It's 0.73%. You have to divide 0.73 by 100. So 0.73% is equal to 0.73 divided by 100. Also, you could move this decimal point over 2 places and put 2 filler zeros in. Put a 0 here and a 0 here and move this over. And what you're going to wind up with is 0.0073. Okay, so here, 0.0073 divided by n. N is monthly. That's the number of times in one time period. Well, we're dealing in years because this percentage I said was a per year percentage, right? And so it's 27 years. How many times does monthly happen in a year? 12 times, because there's 12 months in a year. So we're going to put over 12 to the power of n, 12, times t. Oh, okay, so how many years? That's 27 years. So put times 27. So let's simplify this a little bit. Let's put in 1 minus, so put 1 minus 0.0073 divided by 12. And I get 0.99939. So 24 times 0.99939. And there's also a 1667, but we can stop at this point. I want you to notice something. I want you to notice the difference between the discrete growth and the discrete decay formula. In the discrete growth formula, this number inside the parentheses will always be larger than 1. And the discrete, or the number inside the parentheses here will always be less than 1, 0.999. This is less than 1. And that's how we accomplish growth or decay. When we raise a number larger than 1 to a power, we get a number larger than 1. But when we take a number that's already smaller than 1 and multiply it by itself a bunch of times, it gets smaller and smaller and smaller. For example, if we do 0.9 times 0.9 times 0.9 times 0.9, be 0.9 times 0.9 times 0.9 times 0.9, we get 0.6561. The number's getting smaller and smaller and smaller and smaller. Okay? And that's what happens with decay. So now, to the power of 12 times 27, 12 times 27, that's 324. And now if we plug that into the calculator, 24. Or no, sorry, we want to do 0.999939 to the power of 324 times 24. I get 19.695. I'm rounding there. 695. And now I put million. So the final answer is if it started at 24 million, it's lost value over time, and now it's 19.695 million. Okay? All right. I'm probably going to do one more video where I just do a bunch of examples of problems, and then hopefully you'll have the hang of it. Okay? All right.